Hi grade 11s, we are starting this wonderful section called Trig. You will definitely remember learning the basics last year, and I think the most important thing with something like Trig is the moment something isn't making sense to you, you've got to ask a question. Reason being is that Trig builds quite heavily on basic understanding, and it gets quite tricky by the end of Trig. It really is such a fun section. But the success to Trig is the moment something doesn't make sense, you've got to ask a question. So don't let anything just fall by the wayside. Anything you don't understand, you've got to get in touch with your teacher. Okay, so we're going to start. I've divided up the trigonometry section into a whole series of topics. So this topic 1, which what this video is on the basics from grade 10. Now everyone teaches differently in grade 10. But this is just to kind of bring it all together. We're not going to cover every single thing we did in grade 10 in this video, because some of the stuff we did in grade 10 is going to fall into other topics, and we'll do revision of that within other topics. So basically what this video is about is literally your basics. What is the introduction to Trig from grade 10? Okay, don't forget to take down all the notes. This is such an important section. In Matric, we add on to Trig, but we don't really have a lot of time to go over your grade 11 work. So your notes in this type of section has to be really, really good. So topic 1, the basics from grade 10. Now, as I've said, everyone teaches trigonometry differently. I always approach Trig that there are two almost different definitions of Trig. What happened in the beginning is that mathematicians started to look at right angle triangles. And so this first definition, let me zoom out. This first definition is about right angle triangle trig. This is where Trig started. Trig started because mathematicians noticed things that were happening in right angle triangles. So the first definition of Trig is a definition that only works in right angle triangles. As you can see from below, the second definition I call Cartesian plane trig. Now we'll get to that in a moment, but it's almost like they're completely different definitions. And when you're doing a question, you have to ask yourself, okay, am I working with Cartesian plane trig now, or am I working with right angle trig? Now that sounds quite complicated. It actually really isn't. Okay, let's look at right angle trig. The idea is if you label an angle, in this case I've labeled angle A, I've labeled that theta. Notice this is a right angle triangle. Now the first important thing about right angle triangle trig is that there's always an opposite side. So opposite to the angle is called the opposite side, which we call O. There's always a hypotenuse. A hypotenuse is the longest side in a right angle triangle. It is opposite the 90 degrees. And so the last side which remains is called the adjacent side because it's next to that angle. So that's an A for adjacent. So every single right angle triangle, you can label the sides with opposite, adjacent, and hypotenuse. I always put in the opposite first, and then the hypotenuse, and then lastly the adjacent, because you'll notice that the hypotenuse is also adjacent. So sometimes if you haven't labeled in your hypotenuse, you can get a bit stuck. The next important thing to notice is that the words like opposite and adjacent are prepositions. They're all about telling you the position. Now, these are all with respect to theta. So, for example, if I put an alpha in there, now everything's different. If I'm labeling this triangle according to alpha now, well, all of a sudden, this is the opposite side. So I'm going to erase that now because that's not the point, but I just want to be clear from the start that when you label adjacent and opposite in a right angle triangle, it's all relative. It's got to do with who are you talking about, and in this case we're talking about theta. Now what is sine of theta? The shortcut is we say sin, but it's pronounced sine. Sine of theta means in a right angle triangle, go measure the opposite side, go measure the hypotenuse side, and divide them together. Then what is cos? The definition of cos in a right angle triangle is measure the adjacent side, measure the hypotenuse, and divide them together. And what is tan? Tan is opposite over adjacent. So those are the three definitions that we will use for trig in a right angle triangle. Now, why is trig so brilliant? Trig is brilliant because it doesn't matter what right angle triangle, whether it's ginormous or tiny. If you have the same angle, every single time you work out the opposite over the hypotenuse, you will get the same ratio or the same answer every single time if you're talking about the same angle. Now that becomes really useful, and we'll see that later on. Now, how do you remember that sine is opposite over hypotenuse? Lots of people remember an acronym called SOHCAHTOA, which is sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. So lots of people will write SOHCAHTOA at the start of the exam to remember. I don't remember that ever. I can't spell SOHCAHTOA. I remember SOHCAHTOA, but I just can't spell it. So I remember something that says silly old hens cackle and howl till old age. So that's how I remember how to spell SOHCAHTOA. So I've just gone and written that in there. So silly old hens cackle and howl till old age. And the first letter of every word helps me to remember how to spell SOHCAHTOA. Now, actually, right-angled triangle trig was quite important in grade 10. And what we're going to notice in grade 11 is we start to move very much towards Cartesian plane trig. Because what happened is mathematicians were like, oh, this is wonderful, trig is amazing. But these definitions of trig only worked in right-angled triangles because everything was about hypotenuses. So what they started to discover is that's wonderful, but not every angle falls into a right-angled triangle. And so then came the introduction of something called, I call it Cartesian plane trig. Now, this is almost like redefining the trig ratios. So what they did is, a couple of things first. The x-axis is the horizontal axis, which you know. In trig, all angles are measured counterclockwise from the x-axis. That's what makes an angle. So an angle of theta here would be the angle from the x-axis counterclockwise until this line. The distance from the origin to this point is always called r. Now why it's called r is as you take this arm and you rotate it all the way about the origin, you'll notice that you would form a circle. And so it's called r because basically you would form a radius of a circle. So that's where the r comes from. This point we say has coordinates x and y. So sine of theta in a Cartesian plane is redefined as y over r. Cos of theta is defined as x over r. And tan of theta is defined as y over x. Now in your grade 10 year, they would have told you how mathematicians went from definition 1 and then expanded it into definition 2. Now we don't really have to know that, and so I'm not going to dwell on that. The most important thing is there's 2 definitions of trig, and 99% of the time in grade 11 we're going to be dealing with this one, the Cartesian plane trig. Now how do you remember this? Well, I remember a little saying that it says shield your rear because x-rays tan your exterior. That's what helped me remember this definition. So I've just written that little saying in there, shield your rear because x-rays tan your exterior. So that's the little saying that I remember in order to remember the definitions of trig in the Cartesian plane. Ultimately, I promise you'll end up working with these definitions so much that you don't actually have to remember it. They actually just become second nature. Okay, now again, this might be a little bit rusty for you, and so you're probably like, oh, when do we use these, etc. We'll get there, so don't worry. So far we know that there's 2 definitions of trig depending on what you're working with, and we know what those definitions are. The next thing to look at is what we call the cast diagram. So I'll explain in a moment why it's called the cast diagram. So that's the first thing that people call it. The second thing that I have learned people call it is it's not called the ASTC diagram, it's called the All Stations to Cape Town diagram. So lots of people will call it All Stations to Cape Town, and most people in South Africa will call it the cast diagram. Now what is that about? And this is about the Cartesian plane and the fact that there's 4 quadrants. We will hopefully remember that this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So if I form an angle of theta, and it's in this angle of theta lands me up at point P, which is in the first quadrant, what do I know about the signs? Now all the cast diagram about is are things positive or are things negative? So if you look at the first quadrant here, what would the x value be of p? And what would the y value be? So this is the x value there. So what would that x value be? I'm hoping we all will agree he's positive. The y value, that's the positive part of the y-axis, so this would be positive. And r is the distance from the origin to the point. And so this is always positive. So I've just written a note in there that says exactly that, which means I can immediately go fill in the fact that r is positive no matter what quadrant you're talking about. So let's go back to this quadrant 1. If you look at quadrant 1, x is positive, y is positive, and r is always positive, which means it doesn't matter what ratio you work out, all your ratios are positive. So that's where the a comes from. All ratios are positive here. So as long as an angle is between 0, notice that this is 0 degrees, and this would be, if I move my r all the way up to the y-axis, this would be 90 degrees. So any acute angle, every single trig ratio lands up being positive. So what happens if we drew an angle of theta that went all the way into the second quadrant? So that means an obtuse angle of theta. Well, if I talk about a y value, our y value would still be in the positive region. However, our x value, that would be a negative value for x. So if you think about the definitions of trig, sine is y over r. Now both of those would be positive. So sine is positive in this quadrant. Now you'll notice x is negative. That means that any ratio involving x will automatically be negative because everything else is positive. So cos, for example, would be a negative divided by positive, which is negative. Tan would be a positive divided by negative, which is negative. So the only ratio that's positive in this particular quadrant is sine. So sine is positive. So I hope you see where we're getting this ASTC from. So let's look at an angle of theta that goes all the way into the third quadrant. So this would be an angle, a reflex angle, so between 180 and 270. So if my thing went down there, so P. If you look at this x value, you'll notice this x value is still negative. This y value is now negative. So which trig ratio will end up being positive in this particular quadrant? Well, anything involving r and y, so sine, that would be a negative divided by positive. So that would be negative. Cos would be a negative divided by positive, so that would be a negative. So the only thing that would land up being positive is if you divided by y by x, which is tan. So in this quadrant, tan is positive. Again, I hope you're seeing the pattern. Last but not least, what happens if you went all the way down into the fourth quadrant? So that would be an angle between 270 and now 0. That seems weird. Now notice that 0 would also be exactly the same as 360. So if you did a full 360 degrees, you actually land up where you started. And so 0 degrees and 360 degrees are the same thing. So what happens if theta did that for us all the way around? Well, then I would land up at a point P, and that would be in the positive x-axis region, so this would be positive, but y would still be negative. So what's the only ratio that would be positive in this quadrant? Would be x divided by r, which is cos. So cos is positive. Now, all of this explanation that I've been giving you boils down to one thing. It boils down to the fact that in quadrant 1, all the ratios are positive. In quadrant 2, only the sine ratio is positive. In quadrant 3, only the tan ratio is positive. And in quadrant 4, only the cos ratio is positive. So this is where cast comes from, because we say C-A-S-T. Now, the only thing I think can get confusing there is why do you start in quadrant 4? Who knows? And that's why I often prefer all stations to Cape Town, because that starts in quadrant 1. Now, this idea of this cast diagram, or this all stations to Cape Town diagram, the idea of knowing when a ratio is positive is going to be absolutely huge in grade 11. And so again, if anything in this particular picture didn't make sense to you, ask your maths teacher. We are going to work with this a lot, and so hopefully it'll become a little bit more clear. Now, last thing, which is just a summary before we do a couple of questions, is this idea of special angles. Now, special angles are basically angles that we should know the trig ratios of even if we don't have a calculator. Now, our special angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Now, 0 and 90 we don't really think about because you can't form a right angle triangle with 0 and 90, and so we don't really look at them. So we basically look at 30, 45, and 60. Now, I'm going to be very honest. We actually do not care if you use a calculator. We really don't. I'm hoping that eventually sine, cos, and tan of 30, 45, and 60, you've just practiced so much that they become things you know. But there's nothing wrong with picking up a calculator and using your calculator. What we would have taught you in grade 10 is that mathematicians, remember, they didn't have calculators when they were coming up with trig. So they had to accurately construct right angle triangles. So if you constructed a 45-degree triangle, so there's 45 and there's 45, so if I label the triangle according to this, this would be opposite, this would be my hypotenuse, and this would be my adjacent. And so what mathematicians did before we had calculators is that they accurately constructed this. So they know that sine would be opposite over hypotenuse, cos would be adjacent over hypotenuse, and tan would be opposite over adjacent. So they worked out those particular ratios by accurately constructing a 45-degree triangle. But let me say this again. You can use your calculator. You really can. So let's look at 30 degrees. They accurately constructed this, and opposite would have been 1, hypotenuse would have been 2, and adjacent would have been root 3. So sine of 30 degrees is a half, cos of 30 degrees is root 3 over 2, and tan of 30 degrees is root 3 over 1, which is root 3. Now, if I go and label this triangle according to 60, you'll notice the hypotenuse stays the same. However, now, this is not adjacent, it's opposite. And this is not opposite, this is adjacent. So sine of 60 degrees is root 3 over 2. Cos of 60 degrees is a half, and tan of 60 degrees is 1 over root 3. Now, just to point this out, do we notice that root 3 over 2, sine of 60, is the same as cos of 30? It's almost like everything's swapped. And sine of 30 is the same as cos of 60. Now, that's a really important thing in the long run, so we'll come back to that. Now, again, your calculator can tell you those values, and so I won't know, and nor will I care, whether you work it out on a calculator or whether you just think about it. So really, the only ratio that your calculator will tell you something different is this tan of 60. Now, just be careful if you use your calculator. It doesn't matter if you use your calculator, but just be careful that you don't think that you've made a mistake if you see a different answer in a memo. Your calculator will tell you that the answer is root 3 over 3. Now, why? Your calculator is programmed to rationalize the denominator. Now, that means your calculator never wants to have an irrational number in the denominator. Now, in this denominator, you have root 3. So this root 3 here means my denominator is irrational. Now, your calculator is programmed not to have that. So you might remember the section on surds. How do you rationalize the denominator? If I multiply by root 3 at the bottom, root 3 times root 3 is 3. So I've rationalized it, I've made it a rational number. But what you multiply the bottom by, you must multiply the top by. So 1 times root 3 is root 3. Now that's the only one of these special angles where your calculator will tell you a so-called different answer. It's the same thing though. So when you look at the memos in trig sections, don't always think you're wrong if it looks slightly different. A hint and trick is to put your answer into the calculator and use that surd to decimal button. So you look at it, what it is as a decimal, then put the so-called answer in and check if it's the same decimal, because it's quite possible for surds to look different, I should say. Right, let's just finish off with some examples. Let's do, first of all, this idea of the quadrants. We'll leave the definitions of trig because we're going to use them later on. Let's just look at this idea of quadrants. This question says, in which quadrants will theta lie in the following cases? So in case A, it says, where is cos? And this symbol means greater than 0. Now, all stations to Cape Town. Which quadrants is cos positive in? Well, definitely quadrant 1, because all ratios are positive in quadrant 1. And what's the other quadrant where cos is positive? That would be quadrant 4. So quadrant 1 and quadrant 4. We always use Roman numerals for these quadrants, simply because of where the ideas came from. Okay, let's look at the next one. Where would sine be negative, but tan would be positive? So again, I'm drawing this all stations to Cape Town diagram. So sine must be less than 0. So can't be talking about that because everything's positive there. Can't be talking about that quadrant because sine is positive there. So this particular statement means I'm either talking about quadrant 3 or I'm talking about quadrant 4. But, and, tan must be positive. So if tan must be positive, the only one of these two quadrants left over where tan is positive is quadrant 3. So this is not possible. So now I'm crossing out that one. This is telling me that I can narrow it down to quadrant 3. Now this idea of narrowing the quadrants down to isolate one quadrant if you're given 2 bits of information, that's going to be something that's really important in the next lesson. Cool, let's try some more. Okay, next one. Where will I be if theta is 275 degrees? So this question is just to quickly solidify the idea that the x-axis is 0, this is 90, this is 180, this is 270, and then I'd go back to 360. So if I'm going to 275, remember you go anti-clockwise, so I'd have to go all the way into quadrant 4. So it's just trying to get our heads around the idea of where the angles are in each quadrant. Right, on to these last two. Where is sine positive and cos positive? Well, all stations to Cape Town. Where is sine greater than 0? In quadrant, can't be in quadrant 3, can't be in quadrant 4. So this would be in quadrant 1 or 2, but at the same time, cos has to be positive. So if cos has to be positive, it means that I cannot be there. So this quadrant 2 is no longer possible, and therefore my answer to this is quadrant 1. Last question around these quadrants is, and again, all stations to Cape Town, where is sine negative? So sine is, so that can't be there, that's where it's positive, it can't be there. So I would be talking about quadrants 3 or 4. But at the same time, cos has to be negative. So I can't be talking about quadrant 4 because quadrant 4 is where sine is positive. And so therefore, I must be talking about quadrant 3. Okay, so that was just practicing this idea of this all stations to Cape Town diagram and where everything's positive or negative. We're going to use those ideas quite a lot in the next lesson. Okay, on to just 2 quick questions about simplifying without a calculator. Now, if it says without a calculator, it means that everything must basically boil down to a special angle. Now, I'm just going to put a little star there. Special angles mean you should know them without a calculator, but I'm going to say it again. I don't care whether you cheat on a calculator as long as you show you're working. So, for example, you can't put that entire thing into your calculator and just get an answer. So you can put sine 30. If you can't remember what sine 30 is without a calculator, just put sine 30 into a calculator and check. I know that sine 30 is a half. Now, I know that, but I wouldn't have known if I checked on a calculator or not. Okay, tan 45, again, once you've practiced trig a lot, you know that tan 45 is 1, but you could have checked on a calculator. Now, sine of 90, we haven't spoken about 90 degrees, and we're going to speak about 90 degrees when we start doing trig functions. But I know my trig functions well enough to know that sine of 90 degrees is 1, but you could have checked on a calculator. Okay, now once again, cos 60 at the bottom, Technically, we should know that off by heart, but you can check on your calculator and you should get a half. Now, I actually want you to just pause for a moment and check one of these on your calculator, because there are different ways to measuring angles. We measure angles in degrees, but you can also measure angles in radians, and you can also measure angles in something called gradients. And so angles are measured for us in degrees. So just check one of these on your calculator to check that your calculator is in the right mode. Otherwise, every single answer you do in Trig will be wrong. So before every single exam, just check that you've got a little D in the top display of your calculator along the top line. Tiny little D. If you've got an R, that means your calculator's working in radians, which is bad. And if you've got a little G, your calculator's working in gradients, that's bad. Now, to change out of these, you just go Shift on your calculator, which is in the top left-hand corner, and then you click Mode, which is in kind of the top right-hand corner, and then you'll see it'll give you examples, it'll give you options of, it'll give you lots of options, but you'll see there's an option of Deg, which stands for degrees, Rad, which stands for radians, and Gra, which stands for gradients. So you want to be in Deg. So if you ever find yourself in something else, you want to be in Deg. Okay, now if we just pop back to this question, you could put that in your calculator again, but basically I know that 1 times 1 is 1, and so a half times 1 is just a half, and then a half divided by half, so this actually just becomes 1. So again, I wouldn't know whether you did each of those individually on a calculator. As long as you don't put it all in on your calculator, that's fine. Okay, last question just to wrap up. Sine squared of 60. Well, okay, now I chose this example because of the notation. We put the squared there, but this actually means sine of 60 all squared in a bracket. Now please don't forget there's no such thing as sine. Absolutely nothing. Sine, you have to have sine of an angle, because you have to say to the calculator, I'm taking 60 degrees and I'm working out opposite of a hypotenuse. So there is no such thing as sine on its own. It's always sine of 60. So, or sine of 30. You have to have an angle. So don't think that I'm squaring kind of sine there. It's basically the sine of 60 squared. So sine of 60, which I would cheat on my calculator if I didn't know, is root 3 over 2. So that's squared. Now this is plus, and now this means the sine of 30 all squared. And you can pick up your calculator and you'll know that that's a half squared. And now again, if we're technically not meant to have a calculator, we should probably show some working. So this first term, root 3 squared is just 3, and 2 squared is 4. The next term, 1 squared is 1, 2 squared is 4. So I get 3/4 plus 1/4, which is 4/4, which is 1. And so, as you'll see, I could have cheated with my calculator a little bit as I went. Cool, now that's basically a fairly brief nutshell of pretty much everything we learned in grade 10. So the idea of 2 separate definitions, and we're going to use those definitions in a moment. So we haven't practiced that. Then there was the idea of which quadrant what ratio is positive in, and then the idea of special angles. So that's a wrap of grade 10 revision. I hope you've got some good notes down, because I can't stress enough that this is such a vital section to be on top of at all times and to have wonderful notes.